So I'm going to talk to you all about compressed sensing. It's not the 24th, but okay, so I'm going to give you a scenario. I come home and I, for some reason, decide I would like to store the Twilight Saga on my computer. And I obviously, the simple way of doing it is to store each character. So it begins with some nonsense, and I store those characters. That's a simple way of doing it. But there's also a way using compression, and the idea there would be, instead of storing each character individually, think about each word and map each word to a number, and then store those numbers. So for example, if I want to, Twilight's copyrighted, so I couldn't actually get an extract from Twilight, but I took something with similar, talent. And you could form a dictionary with the words "the cat sat on mat," and then your sentence would just be 1, 2, 3, 4, 1, 5. And this is a significant reduction in the amount you'd actually need to store. Instead of storing 22 characters, you would now just need to store 6 numbers. Okay. And actually, it's the same sort of thing when you compress pictures. We use this dictionary called Wavelets, and the point is that when we convert everything to wavelets, we'll be able to store things more effectively. Most of the values, when we convert to wavelets, will become zeros, so we can just ignore them and only store the important values, and then transform back to our original image. So I took an example of a well-known model. On the left is a picture of me, and then in the middle, you can't really see it with the projector, but there are some values where it's actually like very, very large, and they're normally in the top left of that image. And then you can delete all the values which aren't very large, store that on your computer, so just consider the big ones, and then convert it back, and you get your compressed version of the image, which comes out very, very good, considering in this particular compression, I only stored 1% of the values. So I need those 1% of the values and their locations. That's pretty good. But the real thing, this is just compression, and the real thing here is using compression to improve, say, MRI scans, and that's what compressed sensing is really about. So I'm going to treat the MRI scanner as you put an object in your MRI scanner, and what it will do is it will give you a discrete Fourier transform of an image of that object. And this is just a mathematical model of the MRI scanner. I'm told it's an accurate way of describing it. I think realistically you want to use the full Fourier transform, but we'll treat it as a discrete Fourier transform. And the point is, the discrete Fourier transform, we give it a frequency, and then we ask what is the transformation at that frequency of the image. And we can do this at lots and lots of different frequencies. And by getting all the frequencies, we will be able to recover the image. So yeah, if we know every frequency will be fine, we can recover the image exactly. We can just inverse the discrete Fourier transform. The problem is time. Every time you ask an MRI scanner to take a frequency and the information at that frequency, it takes time. And the idea would be to reduce scanner acquisition time. If you're just going to compress the picture anyway, do you really need to take in all the samples? So the problem is, if you only took in some frequencies, there are lots of different images which could fit your data. And the real question is narrowing it down to the one you actually want. And this is all called subsampling. And the key here is, you know your picture is compressible when you convert it to wavelets. All natural pictures behave like a picture of me. They're very compressible when you convert them to wavelets. It doesn't matter what you take a picture of. And you look for the most compressible picture that fits your MRI measurements. And in doing so, you should get good results. So I took a picture of a brain, although admittedly if that looks like a brain in MRI scans. But this is a standard picture that's used in compressed sensing. And the point is that I sampled only at the frequencies represented by the white dots. And I was able to get the original picture back exactly. And that corresponded to 20% of the samples. And to be honest, the sampling pattern I've taken, it will do well with whatever picture I give it, not just the brain. Okay, so that's basically what compressed sensing is about. There are still a few questions that remain. Given a picture, so you know what your picture is, what is the best way of picking your samples? So you saw earlier I picked them all in the middle. Is that the best way? Is it possible to do better? Conversely, if you're given a set of frequencies that you're allowed to sample at, which pictures can you recover? And those are kind of the two fundamental questions I try and look at in my PhD.